In part B of this problem, we have that the curve has a vertical tangent line at one point. So if we're looking for the slope of a parametric curve, that's given by dy dx. And dy dx in a parametric curve is found by dy dt over dx dt. And that would have a vertical tangent line, or that would be a vertical tangent when the denominator is equal to 0. So when dx dt is 0, dy dx is undefined and the curve has a vertical tangent at that point. So all we really need to find for part B is where dx dt is equal to 0. We'll bring in the calculator to do that. So if you recall, dx dt is the arc sine. So if we come back to that is equivalent to y1 here. So we turn that on, turn everything else off. We zoom, standard, and what we're looking for is where that has a 0, and there's only one. We find where that has a 0. The left bound is x equals 0. The right bound is somewhere over here. And the guess in between there is that x, or in this case it's t, equals 0.693. So recall what this is saying. It's saying that dx dt is 0 when t is equal to 0.693, and that will force the ratio of dy dt over dx dt to be undefined, or to have a vertical tangent at that particular point. And that's actually point B. Then in part C, we have this function m of t, and it denotes the slope of the line tangent to the curve at x of t, comma y of t. Now m of t really is just dy dx, which is dy dt over dx dt. Now we want to write an expression for m of t in terms of t and use it to evaluate the limit as t goes to infinity of m of t. So as I said, m of t really is just dy dx, which in turn is just dy dt over dx dt. And since this is a calculator problem, I don't think that you really need to write all that stuff down at this point. So we have the expression for m of t. It's just dy dt over dx dt. And now we want to evaluate the limit as t goes to infinity of m of t, which is... Now I'm going to suggest that the easiest way to do this would be again to use our calculator in a way that we have used it at the beginning of the year when we were trying to evaluate limits numerically. And so what we really want here is y1 over y2. So I'm going to turn off y1 and come in, and in y4 I'm going to set up, actually it's dy dt, which is y2 over y1. So vars, y vars, function y2 divided by vars, y vars, function y1. And what I want to do with that is to see what happens to that as t, or in this case x, becomes infinitely large. And the way I'm going to do that is go into table set, and I'm going to set up my limit, my independent to ask, and then go to table, and I'm going to try larger and larger values of x. So if I select x is 100, then x is 1,000, then x is 10,000, then x is 100,000, you can see that I'm getting closer and closer to 0. So that's 1,000,000. And I'm getting closer and closer to 0, but I'll never hit that. And so my limit is 0. Now it doesn't ask us here to show our work or to demonstrate anything, so it's fine to use this method of to use the calculator numerically to evaluate that limit. And we're done at that point with that question.